Hello geniuses! Last time I talked about the steps one would take to process their data. This time we will dive into how to build our AI model, or as I like to call it, the fun part. Now before we dive into coding our model, I want to talk about the frameworks you can use to build your models. The most prominent ones are TensorFlow by Google and PyTorch by Meta. If you remember from the last video, I imported a library called TensorFlow right here, so you can probably guess which one we'll be using today. There are pros and cons to using either one, but if you know how to use one of them really well, your knowledge will transfer pretty well to the other. I've been throwing out the words AI and machine learning pretty interchangeably, but in reality they are not. If you watched my last video, you would understand why. But what we really want to focus on is deep learning with neural networks, which is a subset of machine learning. Predicting what number a picture represents doesn't need to be done using neural networks. In fact, other non-neural network machine learning models can do this task as well, such as logistic regression, support vector machines, k-nearest neighbor, just to name a few. I also recommend watching Stanford's Intro to Neural Network lecture for some insight into logistic regression in neural networks, as well as Andrew Ng's machine learning course. These machine learning algorithms can usually perform the tasks thrown at them pretty well, and are usually faster to train and require less computational power to perform the task compared to neural networks. However, the state-of-art performances are almost always by neural networks these days, so why settle for what those weak models can do when you have the beefy neural networks, right? The basis of neural networks relies on these nodes or neurons. Now, these neurons would take inputs. I will attempt to draw, no. So let's say this box represents a neuron here. Neuron, there we go. And there is a input, which we'll call I, and output, which we'll call Y hat. Now, what happens here is that these neurons will take inputs and output a number as well. So you can think of a neuron as a big function. Now first, an input would enter the neuron, will be multiplied by a weight. So the function would be multiply by the weight. And then this whole value will be added to a bias, which we will call B. Now with this whole expression, it will be fed into a function, which we will call F. And this function would finally spit out the output, Y hat. Now, in mathematical terms, it will look something like this. The output, Y hat, would be equal to the multiplication of the input I and the weight W added on to the bias B and put into a function called F. In reality, actually though, each neuron will actually receive multiple inputs. So we can think of it as I0 with I1 with I2 all feeding into this. Now what would this look like? I mean, in reality, there will probably actually be more than 3 inputs, but let's say that there are only 3 inputs for this. Y hat in this case would actually equal to still the function, but inside the function, it would be the sum of all the inputs multiplied by a weight and added to a bias. Now the number of these inputs will be dictated if I say this number k in this sigma function here, so let's say k is equal to 1 first, or let's say 0 actually, then it is equal to 2. So that would have us with 3 inputs, which in this case corresponds to our 3 inputs over here. If you watch the 3 blue 1 brown video on neural networks, which I will link, he explains it with some very nice visuals, at least better than what I have here. Now, you may be wondering how we can get these values of weights and biases. Well, first of all, the very inputs in our case are the pixel values in the number images. However, the weights and biases are determined through a process called gradient descent, which is essentially the AI's way of learning through trial and error. I'll explain this more in depth later on. Now, without all this jargon, all you really need to know is that a neuron takes in a number and spits out a different number. What makes it act intelligent is that it can spit out numbers that eventually can help us solve problems. Like in this case, it would spit out numbers that can correspond to the image. Now, to help you visualize what neurons are doing in a whole network, I've made this diagram here. You can see that each circle here is a neuron, and the lines are the links between each neuron. See, it's a big network of lines. So for the first column, in reality for our use case, there would be 784 of these circles in this first column, but I can't really fit in 784 circles in this diagram, so there's only 28 for the inputs. Now you can see the input nodes are fed into a next layer of neurons, this layer, through lines, which you can think of as a weight that we learned earlier. You can see clearly here that each neuron takes in multiple inputs. Like, look at all these lines just crowding in to fit into one neuron. For example, this neuron, all of these neurons in the first column have a line into this one neuron. That's the same for all these ones here. Of course, for our next layer here, the previous layer would act as the inputs. So each one of these neurons in this layer would have 5 inputs going into it, until we get to the last layer where there are 10 nodes with outputs for the number 0 all the way to the number 9. So what happens to our input image is that it gets squashed into 784 numbers in a line, which are then fed into the neural network that I just showed. So let's look at the top column of our image right here. There will be 28 pixels in the top column. In the first one would go into our first input node. Second one would go into our second input node, and so on until the last pixel here would be our last input node. And there would be 784 of these. And then they would connect to our neural network, which we had 5 nodes for each column. Look, something like this, right? I mean, you get what I'm saying. It's an awful drawing, but anyways, that would be how it would connect. And there's one more term I'd like to teach y'all, which is hidden layers. So hidden layers are basically these 2 layers in our case here. So they would be layers that aren't the input layer like this one, and wouldn't be the output layer with the 10 neurons. So these would be the hidden layers, and those layers would be the ones that the model is actively adjusting to our desired outputs. So finally, we can get into some code. The first thing we want to do is to get the model function from TensorFlow. So we would create a new cell, and then we would define the model as tf.keras, the models, and we want to pick the sequential model. We pick the sequential model because right now our model just does a feed forward, like it just goes down. Now you'll find it funny, but some models go like sideways and like in all different places, but our model, like you've seen, just moves in one direction, and we can just use the sequential model for that. So for our first layer, we need the flatten layer, which is called as keras.layers, and then we have the flatten layer. And then we need to call the input shape. If you recall, the input shape would just be the 28 by 28 pixeled image. Now for the next layer, it'll be our first hidden layer, right? With 5 neurons. So we would want a layer, and this a neuron basically, they're called using the dense layer function. So we would do that, and then we would have 5 neurons. Now dense layers, they're also called fully connected layers. And the reason why they're called that is, well, they're fully connected. So we would have 5 neurons in here, and if you recall, our next layer is also 5 neurons. And then our final layer is the output layer, which is also still a dense layer. And this is how we define our simple neural network. Now, there's still one more special thing to add, and they're called activation functions. You only need to add them to the hidden layers and output layers. Remember the function in the neuron? This f here. Now those are what activation functions are. So for our first hidden layer, we want our activation function to be called ReLU. Now ReLU is an extremely popular activation function that is used in a variety of models, and it's extremely easy to understand as well. Essentially, it takes the input, performs the absolute value process on it. So if the input is -1, ReLU would return +1. And if the input was, say, 1000, ReLU would just return back 1000. And we would apply the same activation for our second dense layer, hidden layer. And for our final output layer, there is a different activation function we would use. My spelling is really bad. It's called softmax. Now, this softmax activation function is a bit special. Now, for those of you who are visual learners, here is a graph of the ReLU function. You can see here that if the number that is inputted is less or equal to 0, then the ReLU function returns 0. And if the input is bigger than 0, then it just returns the input. In short, what the softmax function does is it outputs a probability distribution. If you recall, we have 10 numbers that we are trying to predict. So the softmax function essentially gives us probabilities of how likely each number corresponds to the actual number. For example, if the actual number, an image of a 4, something like this, as our input. Softmax function might give us an output like this. So for our first number, 0, it might give us just a probability of 0. Second number 1, it might give us a probability like say 0.05. Say for number 2, it'll give us 0. Say for number 3, it'll also give us a 0. Number 4, it'll also give us, actually no, it won't give us a 0 because it's the actual number. Let's say it'll give us 0.7. For 5, maybe it'll give us another 0. 6, maybe it'll give us another 0. 7, maybe it'll give us another 0. For 8, another 0. Actually, wait, how many do I have now? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So for 9, I specifically drew the 4 that kind of looks like a 9. So it might have, say, a probability of 0.25. Now, if you look at this, the 0.05, adding on to the 0.7, adding to the 0.25, this actually gives us 1. So whatever softmax gives us, the probabilities, it will always add up to 1. And essentially, if this was the output that the model would have given us, then we could see that the model is saying it is 70% sure that this is a 4. So the model, if we were to take the most likely number, it would say the number is a 4, which would be correct. Now, after making a model, I like to use the model.summary function. Looks something like this. And basically what this line would do is it prints out some useful information, some useful numbers, help me get a sense of what the model kind of looks like. So here we can see the shape of our first flattened layer flattens the 28 by 28 image into a vector of 784 numbers, and for each of the hidden layers it outputs 5 since we have 5 neurons. The last one it outputs 10 since we have 10 neurons. And parameters kind of give us a sense of how big a model is. So basically, the more parameters there are, kind of the bigger the model is. It's a pretty good predictor of it, even though there's some other nitty-gritty calculations to get the full size of the model. I would also like to introduce another function, which is a plot model function. Now you call it like this. You go into the TensorFlow library, into Keras library, utils, and you call function called plot model. We essentially would put our model into there. And we want to see the shapes. Now this is a good function if you want to visualize your model. So essentially, you can see that each of our layers is kind of into a box. Now, for a simple model like this, it's rather obvious what it's going to look like, but with more complex ones, it is important that you grasp what each layer is doing and which inputs go where and which outputs go where. I would also like to clarify something about sequential models, what we define here, which is that it only can be used when each hidden layer has one input layer and one output layer. For example, this hidden layer has this input and this as the output, and this layer has this as the input and this as the output. Now, this means that we would have to use a more general model calling if we were just going to build a more complex model. Like, say, if there were 2 images for input instead of just 1. Next, we will choose an optimizer. Now, one of the most used optimizers is Atom. Did you remember when I said that the AI chooses the weights and biases for each neuron? Well, the Atom optimizer does just that. Now, the theory of optimizers is pretty complex, but the goal of it is to find weights and biases that work best for the model. We can see this in a visualization of a ball rolling in between hills. Something like this. Now, the determination of how good a model is a metric called loss. Now, for these visualizations here, loss would be essentially the z-axis here, or basically how deep these holes go. So essentially, the less the loss is, the less mistakes the model is making, which is good. The more the loss is, the more mistakes the model is making, so that's bad. What we want the ball to do is to roll to a place where the loss is lowest. And for 2D visualization, it's something like this. The y-axis would be the loss. And we would want to get to the global minima here, which is where the loss is at its lowest point. Now, there is one parameter I want to introduce, which is the learning rate for optimizers, which controls how far the ball moves each step. So essentially, if the learning rate is very massive, then the ball might move in big jumps. But if the learning rate is very small, it will move little by little. Now, this process that is happening is called gradient descent, which when done for all of the layers in a neural network is called backpropagation. If you want a more in-depth explanation of gradient descent and backpropagation, once again recommend the 3 blue 1 brown video on it. But enough about rolling balls, let's put this optimizer to use, shall we? So for the code, we would want to use the variable optimizer equal to TensorFlow.rs optimizers.atom. We will be using the atom optimizer. And the parameter that I introduced, the learning rate, we will set it equal to 0.0001. Now the default that TensorFlow sets it to is actually 0.001, but for this dataset, I've found success with a smaller learning rate. We run this and it runs with no bugs, so that's nice. Now next, we will compile our model. We will do model.compile, and the loss we will set to categorical cross entropy. Cross entropy. Now essentially, this categorical cross entropy algorithm, which basically takes the output of the softmax function and sees how close the output is to the real number. And this is the function that gives us our loss. Remember, the lower the loss is, the better. Now for the optimizer of our model, we will set it equal to the optimizer that we just defined over in this cell. And finally, for metrics, we will have accuracy. Now, the accuracy is pretty easily calculated. Say the model predicted the numbers right for 99 cases out of 100. Well, that would be 99% accuracy. So accuracy is better when it's higher. Finally, we can train the model.fit. So we set the history of the training, model.fit. So the first parameter that we need to put in is the input data, which would be train x as we have defined before. And the second parameter are the labels, which is train y. Now is the number of epochs. You can think of epochs as how many rounds the AI trains for. We'll put in 5 for now. As for the batch size, a bigger number lessens the amount of data retained per epoch. So we will set that to 10 for now. And a validation split will be equal to 0.2. And a validation split splits the data into an untouched set to verify our model on. Now, an important distinction must be made for training, validation, and test data. You can think of the training data as a homework you do for a class. You can read over your homework and do it as many times as you want, and you can essentially master the questions on your homework if you do it for enough times. However, the validation data are like quizzes. You don't know what the questions on the quizzes will be, and they are a better indicator of your true knowledge and capabilities. As for the test data, you can think of it as a big test, which is the final test of your model's capabilities. So here we are at the fun step, which is train our model. So press this button, hope for the best. Great, it's training. So look at our first epoch. Now the numbers here is how much data is being looked at in the training epoch. So it's 4,800 images. Now this number here is how long it took to run one epoch. And the accuracy, well, is the accuracy. The loss is the loss. Remember, the higher the accuracy is, the better. The lower the loss is, the better. And what you really want to see is the value accuracy. Now, what the value accuracy tells us is the accuracy for the validation split. Now, if you remember, the model is only trained on the training data, which is reflected in this accuracy. The validation data is not, like, the model doesn't train on that data. So this accuracy loss reflects what the actual model's capability is, like, much better. Look at the loss, we can stretch there. Here we can see that it decreases nicely, the loss, and the accuracy increases nicely as well. Now, to fully max out the capabilities of this model, it would be much better if we trained it for longer, but I'll leave that up to you guys to do. So I've taken the liberty of training the model for 20 epochs just to get some better accuracy. So the final thing, what we want to do is we want to evaluate the model with our test data. Now, if you remember, our test data is essentially the final test for the model to test its capabilities. So it's equal to 1. Now, when I say the batch size is equal to 1, that means that it's basically testing on an epoch for all the training data. Now, essentially, when I set the batch size to 10, it's basically dividing, like, the amount of total training data by 10. So we evaluate this. And an accuracy of around 84%. So basically, if you give the model a image of a number, it'll get it 84% of the time correct. So not too bad, but our model definitely can be improved. Now, for example, what we can do is we can increase the neuron number for each of these layers. And also we can just increase the number of layers as well. Instead of 2 hidden layers, we increase it to 3 hidden layers. And so instead of 5 neurons, we can have like 1024 neurons, or maybe just 4, or maybe just 8 or 16, or whatever you want, right? And that's the fun about like making models like this. You can kind of tune the hyperparameters, play around with different activation functions. For example, leaky ReLU is also a pretty famous one. You can try this. And also you can try different losses and tweak the learning rate, the number of epochs, the batch size, the validation split. There's a lot of things you can tweak to make the model better, and I find that pretty fun. So hopefully you do too, and have fun building AI.